Lesson 1-1, representing data using matrices. So now we're in module 11. What is a matrix? It's a rectangular array of constants, variables, expressions arranged in rows and columns, enclosed in brackets. Each value within a matrix is an element, and its position, so this is important, that tells you something. I'm going to actually flip ahead a little bit, show you guys an example matrix. So it's one of the first examples we're looking at is they have these different cities and different data ranked within the city. Right? So like population, income, house size, rent. So okay, so in one of these cities might have a lot of variables associated with it, right? Here are four, right? These columns, right? Now, how can you compare these cities? Well, you can put all this data in a table like this, right? And eventually you can use this to do it, right? There's other things you can do with matrices like find determinants and right multiply them by right, different things. So you can do different things with the data. But right now, what we're doing is we're just organizing these matrices, right? How can you do this, right? Uh, I don't have my economics book with me, but when I took economics class in college, you'll see, well, pretty much tables that look like this. Okay? So, say like an economics question, like a policy question might be like, if we implement such and such policy, would that be good or bad for, say, for like income or an unemployment rate or something like that? And then when you have all this data organized in a table, you can do math with it and make sense of it, organize it. Okay. So okay. Actually, okay. So we got dimensions within a matrix. M rows and columns is called an M by N matrix. Okay, so you might say like a 3 by 3 matrix or a 2 by 2 matrix. Okay. Actually, here I do have a physics example for you guys too. I'm not sure. Let me show you guys a physics example. So, say you're using this wrench to turn this nut, and the physics term that applies here is called torque. That's with this Greek letter tau. Oh, here we go, torque. Okay. Right, so like a turning moment. And could you imagine that the more you press, like the harder you press, the greater force you put on it upwards, say in the counterclockwise direction, that might make it easier to turn this, right? Or what if you had a longer wrench? I think that could help too. Or hey, what if you align your pushing force in this radial arm at a perpendicular angle? So this angle theta goes to 90 degrees. All that could help you increase your torque, which would help you, say, loosen this nut. Right? Uh, Now here we're looking at an XY plane, but what if you went fancier? What if you did like in 3 dimensions? Ooh, so look, I have like X, Y, and Z axis. It's called I, J, and K, but it's really X, Y, and Z. So you have this nut at the origin, and you have this wrench oriented at some weird angle. And what if you push on it at some weird angle, also some different weird angle? Okay? How much? What kind of torque is that going to put on this nut though? Okay? And oh, there's a matrix involved here. Now, actually, what you're looking at is called a determinant. So it's a few sections ahead of where we are. Okay? But you can take this data, organize it in a matrix. What's this radial arm? What's this force? What angle is this at? Okay? To make sense of what is the torque, not just magnitude, but also the direction of that torque. Okay, so that's a good physics example there. Okay. Right, so like this matrix, okay, so we're back to dimensions and element. Right? So it looks like I see 2 rows and 3 columns. So I would call this a 2 by 3 matrix. Oh, there it is. Matrix A is a 2 by 3 matrix, 2 by 3. Okay. So go like that. All right, if you see a square matrix that has the same number of columns and rows, like a 2 by 2 or 3 by 3, like these over here, okay, which have some nice properties to them too. Okay, so let's get back to this example, but we're comparing these cities. Okay. All right, we got a question A, B, and C. So question A, use the matrix to organize the data from greatest to least monthly rent. Remember, we are looking at these variables before. We got population, income, house size, rent for these different cities. So uh, okay, we're going to organize it greatest to least monthly rent. Just going to look at this rent column and say, okay, who has the greatest rent here? Is this already, is that already organized like that? From greatest to least rent? You know what? I was going to rearrange these rows, but I don't have to because it's already organized from greatest rent to least rent. Yeah, if I just look at that. Okay. Now, if that had not been the case, like suppose Houston came out to like 1050 for this number. Okay. Well, I'd have to take all this Houston row and bump it up over Philadelphia if that were the case. Okay, something like that. Right, but right now it's already answered. You're looking at the answer right there. Okay. So, what are the dimensions of the matrix? Well, I see 5 cities. That's 5 rows. and I see 4 points of data, right? These four here. Oh, I'm going to call it a 5 by 4. So a 5 by 4. So you could, okay, 5 by 4. All right, what is A24? And what does that represent? So we're going to start here. This would be A11. Whenever they say A, they're talking about some element. In the subscript, it tells you how many rows down and how many columns over to go. So I'm going to go down to over 4. Or so, right? Sorry. The second row in the fourth element. So it's 2, 4, would actually be right here. So what this means is that rent costs $13.76 in Los Angeles. Okay. So is second row, fourth column. There it is. Is the rent is equal to $13.76 in Los Angeles. That's exactly it. Okay. So 2, 4. There's A24 right there. That's what it means. Okay. Okay. Oh, and then they circled it right there. There you go. 2, 4. All right. Example 2, analyze data with matrices. So we have almost all citrus grown in the states is grown in 4 states. Got Arizona, California, Florida, and Texas. All right, so here you go. Here's the 4 states. Okay, and here's how much citrus was grown. It looks like over a year at a time. So we got 2015, 2016, 2016, 2017, 2017, 2018. Okay, all right, so a little bit of a time range here. The value of each season citrus profit, okay, millions of dollars. So for example, Arizona in 2017, 2018, looks like $34 million of citrus there. And so organize the data in a matrix. Let's call it a 4 by 3 matrix because 4 rows, 3 different years, or 4 different cities, 3 different years. We'll do that. Right, so I'm gonna copy, actually, let me get this book back on screen. Okay. Right, so we're going to create this matrix here. Okay, so this is example 2 up here. Okay, I think that's enough space there. Okay. All right, so we got these 4 cities. Oh no, I'll put them outside the matrix because it's not numerical data. It's just naming each row. Okay, so we got uh, Arizona, California, Florida, and Texas. There we go. There's the 4 rows. Okay. Above the matrix, I'll put the data here. So here, I'm just going to shorten this to 2016, 2017, and 2018. Okay, just a little abbreviation there. Okay. Now those are well, categories of times. Right? So I'm not going to consider that numerical data. The numerical data is all this data right here. Okay, so we got 59, 45.7, 34.2, right, 20, 47.5, 22, 21.8, 24, 38, 12, 48, 4, 11, 78, 1, 7, 10, 2, 87, 86, 6, 106. Right. So there's the matrix. Right? I guess I should have brought these brackets down a little bit. Makes sense. Cap it right here, right here. Right, so there's your matrix right there. So really, yeah, just take this data and put it in this matrix form. Okay, yeah, organized in a 4 by 3 matrix. That's a 4 by 3 matrix right there. Got 4 by 3. Okay, add the elements and interpret the results. So column 1, they're saying if you add these 4 numbers together, okay, which looks like, okay, yeah, there's column 1, right? So if you were to add these 4 numbers together, okay, what this total represents, here, I'll go ahead and get a number. Right, 59 plus 20, 47, 5 plus 12, 48, 4, 87, right? So it comes out to 3,435.6. Right? What that represents is all the citrus that was grown in 2016. Well, at least in these 4 states. So we'll consider that to be all the citrus. Okay. So this is all the citrus grown in, I'll say 4 states. And again, we'll call it 2016 as an abbreviation right there. Yeah. Right. So if you have all the citrus grown in that year, that's what that would represent. Okay. Okay, and then column two, some of those numbers, column three, some of those numbers. Okay, you get the idea. I could add these up, could add these up, and the sum totals of each column would represent all the fruit grown in the four states and whatever corresponding year. This is what that would be. Um, Add the elements in the rows and interpret the results. Okay, so what does it mean if I add all the numbers in a row? Let's take these three right here. This plus this plus this. So I'll say equals, let's see, what's 59 plus 45, 7 plus 34, 2. All right. So the numerical value is 138.9. Right? That's millions of dollars. Okay. Now, what that number represents is uh, all citrus grown, well, dollar values, right? Millions of dollars. Right? In Arizona, over a 3-year period. Okay. There you go. Okay, so yeah, so what do these concepts mean? If you add the values in the column, that's all the citrus in all the states in a particular year. If you add all the numbers in a row, now we're honed in on a specific state, but it's over multiple years. All right, so I see that. Can you interpret that? Okay. Mm, right. Example three, creating an incidence matrix. Uh, okay, so it says this branch of or the branch of mathematics called graph theory. Ooh, this sounds fun. Graph theory involves representing relationships by using graphs that consist of vertices connected by edges. Okay. Looks like we have some dots connected over here. So similar idea. The graph to the right has 5 vertices and 6 edges. Okay, because I see points A, B, C, D, and E. So there's your 5 vertices. And I see 1, 2, 3, 4, 5, 6 lines. Okay. And they numbered all. So they label all the points as letters and they numbered all the vertices. Okay. An incidence matrix of a graph has a row for each vertex and a column for each edge. If an edge contains a vertex, the column in that edge is one row, is a one in the row for the vertex. Create an incidence matrix for the graph. Right, so they actually give the answer right here, but here, I'm going to draw this bigger and recreate that. So it looks better for the camera, and also I can explain this as we're going on. Okay. Okay, so we have this funny looking shape. Okay, we're calling this A, B, C, D, E. So there's the vertices. Okay. And then there's some connections. So these dots happen to be connected this way, and these dots connected like this. Boom, boom, boom. Okay, so just taking this picture and I just copied it right here. Got that. Okay. Uh, I have to label the edges, label the edges. I got edge one, edge two, edge three, edge four, edge five, and edge six. Right, so got the vertices, got the edges labeled. Okay. Now let's go about creating a matrix to represent the scenario. Matrix. I set my big old brackets right here. Brackets. Okay. Well, the columns and rows have to correspond to edges and vertices, or vice versa, right? But you got to pick one. Now, your book looks like it's making you tend towards the columns being the edges, so we'll go with that too. You got edge one, two, three, four, five, six. Right? So the rows would have to be representing the vertices. You got A, B, C, D, E. Okay. Now notice that these are just naming the vertices and the edges. Okay, so I haven't actually written anything inside the matrix yet. Okay. Let's do it. All right, so what does this mean here? Well, do you see how what is connected to point A? Let's do this from point A's point of view, and maybe I can fill out this entire row. Ooh, okay. Well, it looks like A is connected to 4 different edges. Edge one, two, 4, and 6. 1, 2, 4, and 6. So what I can do is at the intersection of A and those particular vertices, I can put a 1, so it would be binary. So it's connected to 1 right here. So bing, yes, 2, yes, bing. 3, no, 3's over here. It's not touching us. So, Right, 4, yes, bing. 5 is over here, it's separate from A, so no. And 6, bing, looks like that. Okay. Now that's just one row, right? That's just for A. Now is that what they got for A? You can see this right here. They got 1, 1, 0, 1, 0, 1. Yeah, okay, got the same thing I did. Okay. Let's switch perspective here. What if we're looking at um, edge one? Edge one. What does that actually connect to? Well, this edge one looks like it connects to point A, which we've already got covered there, and also point B, and that's it. It's just point A and point B. So from edge one, this point of view, I can put a yes or one for A and B each, but a 0, 0, 0 for C, D, and E. Let's see, is that what the book has for those? Yeah, it sure is right there. There's the final answer. Okay. Okay, so now that you guys saw that, okay, let's go through the logic for the rest of these points here. Okay. So, yeah, let's just it. So two, this edge two connects to A and C. So A and C, but none of the others. Edge three connects to only C and D. Do you guys notice that every one of these columns is going to have two ones and three zeros? Do you guys see that? Because every one of these points, vertices, is, or sorry, every one of these edges I meant is connected to exactly 2 points. Has maybe beginning point, end point, left to right, left to right. Okay. How about four is connected to A and D? So there's an A and a D there, and then zero and everything else. How about five is connected to B and E? There's a B and there's an E. And six is connected to A and E. So A and E. So the answer should be this, right? Or you could have done this from the perspective of the vertices. Let's take D, for example. D is connected to only three and four. Okay, so go down, look at D. Yeah, I got, oh, that's exactly a three and a four right there and nothing else. Okay. Also, do you guys notice that every single one of these vertices has exactly two ones and four zeros because every single point is connected to the lines. That's it. All right. Is that, yeah, okay. All right, that's synopsis of the book examples.